So yeah, today I'd like to tell you about some work from our group at ETH Zurich, the group of Jonathan Holm on trapped ions. And the first part of the talk will be about some earlier work, and the main thing is about the error correction that we did in the paper from 2022. And then the second part of the talk will be on some more recent work on GKP codes by some other people in my group, two of which are here today. Yeah. So I think there are not so many ion trappers here in the conference today, in the workshop. So first, I'd like to remind you a bit what our system is. So we have an ion trap, which is shown in this picture, and these gold plates are the electrodes, and this is like a few millimeters size, and in there we trap strings of ions in vacuum, and these ions can be spaced by like 10 micrometers or so. And so the two quantum systems that we think about here are the motion of the ions in the trap, and by applying some voltages to these electrodes, we create a harmonic potential for these ions, and this is our harmonic oscillator system. And then the other important system is given by some internal states of the ion, so the outermost electronic potential of the ion. And in there, we can essentially define a pseudo-spin system. And the main controls that we have on this system come from some lasers that we shine on these ions. And with these lasers, we have like, I mean, this is a very oversimplified picture, but the main thing that you need to understand is just that with these lasers, we can do coherent drive to the spin system. We can essentially do what we call a repump, which resets it to 0 state of the spin. And we can detect by fluorescence detection whether the spin is in the 0 or the 1 state. If it's in 0, we get a bright fluorescence with an auxiliary level, and otherwise, if it's in the 1 state, this off resonant and the state is dark. So then the other important element of control that we have in these systems is by tuning the voltages of the electrodes in the trap. So the most important, or let's say the starting point for control is the coherent drive. And so if we shine this coherent drive laser on the spin, we see a spectrum that looks something like this. So we have a resonance at the frequency of this spin transition that's shown. And then we have some sidebands, which come from some motional coupling. And this gives us our basic Hamiltonians coupled to the motional oscillator state. So we have what we call the red sideband, which is a Jaynes-Cummings Hamiltonian, and that essentially couples in an energy conserving way the spin and motional systems. And then we have what we call the blue sideband, which is an anti-Jaynes-Cummings. And if we actually apply both of these Hamiltonians simultaneously, so we drive both of these side peaks, then we get something that looks like a spin-dependent displacement operator, where we can tune the basis of these lasers to also tune the whether we do like a poly X or poly Y operator, and whether we in the Hamiltonian we get like momentum or position operator. And so the first thing that we can do with this, or that we do every day in the experiments, is driving the red sideband, and then by adding a repump, we can cool this system to the ground state. And then if we add an additional laser, actually we can, and keeping the repump on, we can actually prepare squeeze states in this way. And the reason, the simple way to see this is that if you do a squeezing transformation to the lowering operator, you get a sum of lowering and raising operators, and this sum, the coefficients of this sum tell you the powers that you need for the red end of the cycle. So by changing these powers, you can change the amount of squeezing that you get. And now, if you apply both pulses with equal strength, then you get this spin-dependent displacement. So the Hamiltonian is proportional to something like xt, as I've shown here. And then you can think of this as something that separates the motional oscillator state into two wave packets that are in a tensor product with two different spin states of the internal ion spin. And so now if we, like now this is in a almost maximally entangled state. And then if we do a detection, we can disentangle these systems and actually project the oscillator into a pure squeezed cat state. And one important detail here in our experiments is that when we do this type of post-selection, or when we do this type of measurement, we need to do post-selection because when the ion fluoresces bright, so if it's in the spin 0 state, then we actually scatter many photons, and we will essentially put the oscillator into so the oscillator will get some displacement kicks, and we will put it into a highly excited mixed state. So if we do this type of preparation of a squeeze state, for example, then of a squeezed cat state, then we have to post-select only when the readout is dark. And so now using this technique, some former PhD student in our group used this to then create GKP states. So if you just essentially do the same two steps again, like steps 2 and 3 repeated, then you can again split this squeeze state into two separated wave packets. And then by doing another post-selected dark measurement, you will get an approximate finite energy GKP state. And so actually all these things that I've just told you about, there are like multiple papers from our group discussing like these early experiments where we did the squeezing and then also created these entangled spin motion states that are shown in 2, and then also like squeeze cats or cat states. And finally, GKP states from Christoph Blumen, who was here and gave a talk at the last, before last BB2, I guess. Yeah. So now I want to say a bit about this spin-dependent, a bit more about the spin-dependent displacement. I think it's also something that Philippe mentioned in his talk, that there's some different ways of thinking about this. So sort of the way that I mentioned already is that you can think of this as a displacement of the oscillator state, which is dependent on the state of the spin. So that's what's shown here. That's like a first picture you can think of. And that's also just from the operator here. You see that this like, that you can have this picture by just using the eigenstates of X. But the other way of thinking about it is that if you take the eigenstates of Q, then, which are roughly position eigenstates, then this is also can be seen as a rotation of the spin state, which depends on the position of the oscillator. So in that sense, if the spin state is in 0, then if the oscillator is in 0 position, then you have no rotation, and then as you move the oscillator state, you will have some different rotation. And so these two pictures are I'm going to use these two pictures to kind of explain how we did some experiment, well, essentially state preparation and also pair correction. So actually using this idea, we can improve this sequence here because we actually don't really need to do these measurements. Using the fact that you can rotate the spin depending on the oscillator state, you can actually replace these post-selected detections with more spin-dependent displacements where you disentangle the two systems, and then you can actually deterministically create the GKP. This was an idea from a paper by Jacob Astrup, who's here today. And something that really was a nice improvement to our experiments, because before this we were using post-selected states. And so now I'd like to talk about the error correction. So initially, when we saw the results from Philippe and others when he was at Yale, we saw this kind of simplify, like very minimal sort of phase estimation feedback method, and we thought it's really nice. But if we just naively wanted to do this on our system, it would involve these three operations. So the first operation, this spin-dependent displacement, is fine, that's what I've been mostly explaining so far. But then the displacement we can do with a harmonic voltage on our trap. That's also fine. But of course, if we have to keep doing these post-selected measurements, it's not going to be a feasible scheme for error correction, because we will just have a lower and lower probability of having a usable state. So then actually Jonathan my supervisor had the idea to replace this with a circuit that looks like this. So we just replaced this measurement and classical feedback somehow by a second spin-dependent displacement, which depends on the same spin states in some sense. And then we just reset the system with a repump. And this actually just, you can think that it will be an average over the two possible measurement outcomes. And that works because for this error correction scheme, independent of the measurement record, you always want to stabilize to the GKP manifold. So if you just average, you will also GKP over. You will also stabilize to the GKP manifold. So this was essentially a small adjustment to the scheme from the work that Philippe was on, and that made it possible for us to think about doing it in our system. So now I just will give a brief explanation how we think about this error correction sequence, which is essentially the way it was explained in Philippe's paper. So thinking again about these two pictures of the spin-dependent displacement, you can think that if you start in a fully mixed GKP state, which is in the manifold of the error correction sequence, then we first do this spin-dependent displacement, and which is like a displacement by the stabilizer of the code. And if you think of the picture where this is a rotation of the spin depending on the position, then you can think that the spin state gets rotated according to these. So here I plot the probability of the Y measurement as a function of the position of the oscillator. And a nice way to think about the post-measurement state, which was shown in Philippe's paper, was that you can think of this as a Bayesian process. So the initial state, which is in black, gets essentially multiplied by the probability of the spin measurement outcome conditioned on the position. And then you see that this does like some sort of sharpening, that you project your code more and more into the infinite energy GKP state. And then you also have to apply some feedback. And these, I also mentioned that these parameters are the ones that were sort of, I think, if I understood the experiment explained by Vlad, they started with these parameters and then optimized them further. So the thing is, I guess, yeah, the other part of this is that if you think of the other picture of the spin-dependent displacement, that it will do a displacement in momentum depending on the spin state, then you see that in the P quadrature, you actually split the state into two wave packets, which spreads it out. And then I drew some little pictures to see what happens if you do this on the ground state. So for the full error correction cycle, first you have to apply this in Q, and then you do the same thing in the P quadrature. And you see that if you repeat this, you start to project the code, the state into the GKP state. But if you keep doing this, you will essentially keep increasing the energy of your state, because this sequence is essentially designed for the infinite energy GKP states. So the idea in Philippe's paper to deal with this was to add an additional sequence that looks like this. I've now written it in the form of a repump as we do it, which limits the energy of the state. And it's a really nice idea that you can just use the same sort of modular measurements but with a much smaller displacement here in the first step, so that you get a much broader oscillation of the spin as a function of position, and that essentially trims your state. And now my supervisor, Jonathan, had the idea that maybe we can combine these two things into a single step in this way. And what was really interesting is that also around the same time, Betsy Stroyer and Steve Gervin's group came up with the same sequence by considering finite energy GKP states and doing error correction on those. And essentially, this was a trotterization of the ideal operator for the error correction. And the way we came up with it was really understanding it from a more operational point of view. And it's essentially by thinking of it in the same way as what I've explained to you already. So always thinking of the spin-dependent displacement as either a rotation of the spin depending on position or momentum, or also thinking it as in the other picture that it's a displacement of the oscillator that depends on the spin state. And so this first short pulse, essentially what you can think that it does is that it's a displacement in momentum, which is very small, and you basically can't see it on this picture, I think. But what's more important is that it pre-rotates the spin of the spin state depending on the momentum of the state, so that you can think that here, these states here have a high probability to be in the minus x state, and these states here have a high probability to be in plus x. So that when you apply the second independent displacement, shown in red here, then you will actually displace these states here back towards the center. That was our way of thinking about it. And that's also plotted here, essentially. Like if you don't do this first independent displacement in orange, then you do this, which is the first two plots here. And otherwise, if you do this pre-rotation, then when you do the second spin-dependent displacement, you will have this refocusing, and then you will maintain the envelope state. And this is just slightly zoom in after one cycle. Not so easy to see the difference after one cycle, but after many cycles, the difference is quite big. Okay, so then just to recap a bit the like what we've done here with this GKP error correction. In some sense, you can think of it in a picture like what I've shown you in the beginning, that if you, like I said, if we just drive the thread sideband and repump, we do sideband cooling in a dissipative way, and then if we do these blue and red, we can do this squeeze state pumping. And now in some sense, we've just created a sequence that does a sort of grid state pumping. Essentially, we've just changed the unitary between these three things, and we're just now pumping into the GKP manifold. And so when we applied this in the experiment, then we see that the state quickly converges into this manifold, and here we plot the stabilizer values. And here we just see if we prepare a GKP state, it decays out of the manifold, but if we continue to apply the sequence, we just stabilize. And so now we also check the logical coherence of these states. So we used this method that I explained in the beginning to prepare some different logical states. And then we applied this grid state pumping. And what we found is roughly a 3 times increase in logical lifetime. So this is not like break even, but since yesterday is a bit of a tricky term. Yesterday, Ivan and I were calling this version break easy, but but essentially what we see is the like factor 3 improvement in terms of this break easy. And what's also you might notice in this plot is that, so okay, the orange and the blue curves are the X and Z eigenstates of the GKP square code. And the green curve, which is a bit lower, is the Y state. And here are the unstabilized and destabilized. And you might ask why the Y state is worse. It's essentially, my understanding is that it's just because it decays faster because it has a √2 increase in the displacement from the origin. So the peaks are a bit further out. So it's more susceptible to the noise. And I think it's also the same reason why or similar reason why it's slightly less robust, even when you do error correction. So to recap a bit from this work and also previous work from people in my group, we've shown that we can prepare GKP logical states through error correction. Krista, I didn't mention it, but she also showed that we can do single qubit gates on the GKP states, and logical readout is quite straightforward from these independent displacements. And so you might ask, what are the next steps? Well, of course, we still have to break even. And we've investigated, like, theoretically a bit how we could do that without even changing the method, like pulse sequence, but just by changing some parameters in our experimental setup, we think that it's possible. If you want to know more details, I'm happy to chat about it. But I think also from the conference, I've already learned some other potential ways that might help. Yeah. And then another thing is to look into having the full set of universal gates, and one part of that which is missing is 2-qubit gates. So the second part of my talk, I'd like to discuss some more recent work on these 2-qubit gates. So in the beginning, I will talk a bit how we think about doing this in ions, and then some theory work from Florentine Reiter and Ivan, who's here today, and they initially had a student working on this for his master's. So the idea is, okay, we want to encode 2 GKP states into 2 ions, and then we want to couple them somehow. And one way to do this is, well, there's already been some demonstration of beam splitter interaction ion traps. So we think it's possible to start with this beam splitter and then try to build up some sort of qubit gate. And we chose to look at the CZ gate, which has also been proposed, like that you can do it with beam splitter and local squeezing in this way. And so the other part that would be missing then is this local squeezing operator. You remember that I mentioned we can make squeeze states using this squeeze pumping method, but that's like a way to make squeeze states, but it's not doing the squeezing operator. So we need some different method. But it turns out that there's also some recent work showing that there is a way to do this squeezing operator by essentially modulating your trap at twice the frequency of the oscillator. And so then this provides some sort of a route to do the 2-qubit gate. And then to go further, we considered an alternative decomposition of this 2-qubit gate. So if you just think of the beam splitter operator, you have P1, Q2 plus P1, P2 in the exponent. And if you do some layers of squeezing before and after a beam splitter, then you can essentially exponentially amplify the effect of the Q1, Q2 term and exponentially suppress the P1, P2 term. So in this way, you can also approximate the CZ gate by squeezing your pre-squeezing and post-squeezing your GKP state. And so this approaches the ideal CZ gate as the squeezing goes to infinity, but in practice, we see that if we apply this to a GKP state with finite energy, where the envelope is defined by, or in this case was 0.3 according to this energy, or this envelope, we find that already with this parameter R around 0.9, we get very close to the ideal CZ gate. And you might notice that the fidelity here doesn't go all the way to 1, but that's actually expected even for a very large energy GKP state, because there is a broadening effect that you can think of as so essentially as you do this let's say, displacement along P of one of the oscillators will depend on the Q state of the other one. And this will create a broadening in the P quadrature. And you can think of this as a convolution. So what's happening is that, let's say, we consider the first oscillator as control and the second one as target. And here we plot the position of the first one and the momentum of the second one. Then essentially this, okay, I think I don't have so much time, so I'll rush through this, but essentially this will displace all the states. Like this single peak will get spread out essentially. And similarly, the broadness of the peaks will also create a broadening of the peaks after the gate. So we see that overall this gives a root 2 broadening, but the important thing is that we keep the logical information during this process. So if we just do error correction, we can essentially recover from this gate. So it can still work. The alternative would be to use finite energy gate. Yeah, this is discussed in the paper, but I don't have time. So there's also a new setup for GKP, and some new people in the group working on that. Stefan, Martin, and Moritz, who's here. And they've already demonstrated this squeezing sufficiently for the gate. And then the last thing I want to mention is just that in the long term, this architecture may not be the easiest one to scale because you can only make linear strings of ions. So we also have an idea for 2D, more scalable architecture using penning traps. And there we've already found like very low heating rates compared to even the setup where we did the GKP error correction. So that looks promising. So yeah, just to thank you from my group. Here we see the people working on the new GKP state, and those are the people working on this penning trap setup. So yeah, happy to take questions.
Thanks for the great talk. I wanted to ask, it sounds like the 2-qubit gates, you will have GKP encoded with 2 trapped ions in the system.
Yeah.
Would it be possible to have a single trapped ion where you have a GKP qubit encoded in 2 or maybe even 3 different motional modes and use just one ion to mediate beam splitters between those modes?
You could think about doing this. The way we're considering doing it now is rather to use 2 ions, just because for a scalable scheme, in the end, we'll need to use more than 1 ion. So we're going to try and do it with 2 ions. And there, the idea is actually to have it, the GKPs are encoded in some radial modes. And the idea is then to couple those 2 radial.
Okay, thanks.
For the game.
Just to add up as well to the answer, like when you do it in 2 motional modes of the same ion and you try to make a beam splitter between them, you will have to transfer the information from one ion from one motional mode to the ion, and then from the ion to the motional mode. And that means you will have a small amount of time where your information is not protected, right?
No, for the 2 ion situation, we're using only the Coulomb interaction. So we never go through the internal spin state.
Yes, hi. Thanks for the great results. I was wondering about your 2-qubit gate, and then you say you basically error correct on both modes. After that, you do like error correction cycles. You use SPS or PSP sequence of the error. And basically you do the 2-mode gate. So now you basically displace one oscillator depending on the other. So you have partial information about the other oscillator as well. So basically, if you error correct on one mode, you will have partial information about the other, and it's kind of information you will not use or throw away. So I was wondering if you thought about how much this limits you, and if you find a way to like use this information as well to feed back on the other oscillator as well.
Yeah, I think actually maybe Evan might be the best person to answer because he worked directly.
It's true. It's just that, as Brennen mentioned in the talk, is that when you read out like the motional state, you will destroy it, at least in our system, in the ions. So I don't think we are able to have the information from the error correction. But it's true that for instance, nothing people would be a thing to investigate.
You know how much is in it?
I will point out just, Ian's talk now. In our group, there is a method in order to read out the motion information directly in certain cases without destroying the information, and also to do a direct beam splitter between motional modes without affecting the internal states of the ions or using those at all. Okay, I think we have time for one more quick question if it's really quick.
Yeah, thanks for the nice talk. Do you expect any additional noise when you have these two ions, like additional dephasing that you don't see in just the single ion case?
Yeah, I mean, of course, if you only trap one ion, the requirements are a bit easier, but I don't think there's any fundamental limitation at least.
Thanks.
Let's have another round of applause for Brennen.